Hi, my name is Nick Arnasti, and this is part two of a lecture series about my paper, Greedy Algorithms for Stationary Dynamic Matching, which is with Felipe Simon, who's now a professor at the University of Chile. So if you haven't watched part one of the video, you should go back and watch that. Um, if you have, just a quick reminder of kind of the key takeaways. One is that we're going to show in our dynamic matching model that greedy policies achieve a tight competitive ratio of 1/2, at least under certain conditions. And the other kind of key takeaway that I want you to remember is that we use a very innovative proof technique, which uses a linear program that actually lower bounds our policy's performance. So the content of this second video is going to be to actually go into the proof technique and the algorithm in more detail. So in particular, things we're going to cover is what is this novel linear program that we're using? How do we use the solution from that linear program to define our algorithm? And how do we show that the solution to this linear program actually offers a lower bound for the performance of our algorithm? So let's go right to the first of these. What is the linear program? Okay, here it is. This is the full linear program. Now I know it looks kind of overwhelming, right? So we've got the linear program on the left and just kind of a reminder of our notation on the right. But let's take it one step at a time. So first of all, our decision variables, we're going to have two types of decision variable. One is Ni. This represents the average number of agents of type I that are present in the system. So imagine you've chosen a policy pi, and then your policy induces some steady state distribution over how many agents there are of each type. And I'm letting Ni be the expectation over that distribution of how many agents of type I there are. Meanwhile, Xij is going to be the rate at which we make Ij matches. And being precise, an Ij match means that I'm matching a type J to a type I that arrived before the type J. So there's actually going to be an Xij, and there's going to be an Xji, which corresponds to matching type J to a type I that arrived after J. So these are the key decision variables that we're going to keep track of throughout. For any policy, it's going to induce some n and some x. Now we're going to evaluate our policy based on its objective function, which is just shown here on the left in the orange box, right? Which is we're summing over all types the reward we get from an IJ match times the rate at which we're making IJ matches. So that's pretty straightforward. That's exactly what we're trying to maximize. Okay, the second, now of course, if we could just choose X freely, what I'd want to do is make X really, really large, right? I have a huge rate of all matches, and I'm going to get a massive reward. But of course, I can't just choose whatever N and whatever X I want. There's some constraints. So our first constraint on N and X is going to be basically saying that every agent that arrives must depart. So that's what this is saying. On the right, this lambda I, that's the arrival rate of agents of type I. Now, every type I agent has to depart in one of two ways. Either it matches, or it doesn't match and abandons the system. And so this term here, this sum of x's, is the rate at which we're matching type i's. And this term on the left, Ni mu I, that's the aggregate abandonment rate, right? Because Ni is the average number of agents of type I in the system. And because all of our agents of type I abandon at rate mu I, the average abandonment rate is Ni mu I. And so all this constraint is really saying is that the total match rate plus the total abandonment rate has to equal the arrival rate lambda I. Okay, now we have one more significant constraint we're going to add. And this constraint is really the secret sauce of our linear program. So I'm going to spend some time talking about it. So rather than looking at the exact equation shown here, first I want to just tell you kind of conceptually, what are we trying to capture with this constraint? Okay. And the idea is the rate at which I match a agent of type J to some agent that's waiting and belongs to the set S is limited, right? So in particular, how quickly can I match agents of type J to some agent of type S? Well, first of all, no faster than the arrival rate of J, for sure. I can't match them any faster than they arrive. But in particular, not every type J agent that arrives is going to actually find someone from the set S that it can match to, right? So I need to multiply this arrival rate of J by the probability that an agent from set S is actually present. Okay, so that's the idea, is I can't match J to S any faster than J's arrive. And in particular, even some of those J's won't be able to match. So I need to multiply by the probability that set S is present. Okay, now some of these quantities are actually easy to express in terms of our decision variables, right? So the rate of matching J to weighting agents from S, that's just going to be a sum over all I and S of Xij. The arrival rate of J, that's the primitive lambda J that we're given. Where there's a little bit more difficulty is what do we do about this final quantity, the probability that there exists an agent of some type I in S? We can't easily express that probability as a function of these decision variables. What we can do, though, is note that there's a relationship between that probability and these decision variables. So in particular, Markov's inequality gets us the following, right? So the probability that an agent from set S is present is at most the expected number of agents from set S that are present. And that expected number is exactly the sum of Ni. So this is Markov's inequality. And given that, it might seem very natural to say, well, okay, so I can't exactly express the original constraint I wanted to, but let me approximate this last quantity, this probability, with this sum of Ni, and put that into my linear program. And if I do that, then I have a well-defined linear program, and it's in fact a relaxation of the constraint that I wanted to put in, right? So certainly I have a set of inequalities that any policy you could come up with will satisfy. Okay. But we don't want a relaxation, right? So if we get a relaxation, what we would get out of solving that linear program is essentially an upper bound on the value of any policy. And then we'd have to somehow figure out what policy to use and how to show that it's close to that upper bound. So the real innovation in our work is going to be essentially to show a counterpart to Markov's inequality, which is this key lemma here. Okay, so this key lemma says, at least under the condition that all the mu's in the set S are the same, so all the agents in set S have the same departure rate, then there's a sort of corresponding counterpart to Markov's inequality, which says that the probability that an agent from set S is present is not only upper bounded by the sum of ni's, but it's also lower bounded by that same sum times some constant gamma s. Now, gamma s is a number between 0 and 1, and it has an explicit functional form given here, right? So in terms of the lambdas and the mu's, the primitives of the problem. So once we have this lower bound, then the natural thing to do is to plug that lower bound back in to this inequality that we have above. And that's actually going to give us the constraint that we use in our linear program. Okay. So now, like conceptually, what I want you to think of is instead of a relaxation, now what we've done is we've taken the original constraint we had written in English here, and we've tightened it. Right? We've imposed a stronger constraint than actually what that original inequality says. And as a result, intuitively, this is why the value of the solution that we get from our linear program is actually going to be a pessimistic estimate of the value of the policy, because we're solving with a constraint that is sort of tighter than it really needs to be. So now you might be wondering a little bit more about this lemma, like where does it come from? How do I think about it? What is it telling me? And I'm not going to go into full detail, but I'll try to give you a little bit more intuition about this key lemma. Right? So imagine taking this inequality that we have written in the lemma and dividing both sides by the sum of ni. Okay? Then what we actually get is the ratio of the probability that some agent of type I is present over the expected number of agents of type I that are present. Okay. Now, what you can show is that that ratio, if I don't do any matches at all, right? Suppose my policy is not to match at all. In that case, then this ratio will be exactly gamma s. And that's not hard to show. Looking at the functional form of gamma s, the denominator, sum of lambda I over mu I, that's the expected number in system if you don't do any matches. And the numerator is the probability that there is someone of type I and S in the system if you don't do any matches. Okay. So the content of the lemma is really saying that if you start to do matches, if you have a policy that does some matches, that can only increase this ratio, right? So both the numerator and the denominator are going to go down, but the ratio between them is going to increase. In other words, this ratio is minimized by the no match policy. And this lemma is really the only meaningful stochastic analysis in the paper. Everything else is sort of linear programming, duality, some very, very basic properties like the pasta property. But essentially, this is the only stochastic analysis in the paper, is to show that gamma s times the sum is a lower bound on the probability that an agent from set S is present. Okay, so putting it all together, that gives us this linear program, which I already showed you, but now we can look at it again. Now, the only thing I want to highlight here is I've introduced a third set of variables, but these are really just slack variables. So kind of originally we had this second constraint as being an inequality. Now we've made it an equality by just adding non-negative slack variables. Okay, so that's our linear program. It's a new one. We can solve that linear program. And once we have a solution, the next thing I want to tell you about is how do we actually use that solution to identify a policy? Okay, so the idea behind this is I've got a solution to this linear program. And in particular, we had a lot of constraints in that linear program. So for each type J and each possible subset S, we had a constraint with the gamma S times the sum of the ni's. So I'm doing here an example where I suppose that the type space, there are three types, right? So then the number of subsets S that we have to consider is essentially 2 to the 3. So you'd say 8, but the empty subset is sort of not interesting. So that leaves us with 7 subsets S to consider. 3 subsets of size 1, 3 subsets of size 2, and then, of course, the full set 1, 2, 3. So what our algorithm is going to do is we solve our linear program, and then we say for type J, which of these constraints are tight? In other words, which of these constraints have the corresponding psi equal to 0? So let's suppose that that's these particular constraints. Then we're going to interpret these as prefixes of J's priority list. Right. So in this example, this would tell us that, hey, type 2 is going to be J's top preferred type. That's what we're going to try to match it to first. If we can't find a 2, we'll be willing to match a J to 3. And if we can't find 3, we're just going to have J wait. Right? So in particular, notice that 1 is not included in any of the sets for which this constraint is tight. And therefore, 1 is not an acceptable match for J. Okay, so that's the idea behind how we go from a solution to our linear program to an actual algorithm. And this sounds great when it works, right? When it's easy to sort of interpret the tight sets in this way. But you might wonder, what about cases where, for example, both 2 and 3 are tight, right? Then which one do I put first? Okay, well, the good news is you can actually show pretty easily that we're never going to have the constraint associated with 2 and the constraint associated with 3 both be tight, because that would actually imply that the constraint 2, 3 was violated. So we didn't have to worry about that case where, say, 2 and 3 were both tight. But we did have to worry about other cases. For example, where we didn't have this nested structure, where like only 2, 3 is tight, but not 2. And so for this, we introduce a definition of what does it mean for a solution to be suitable? And it just means that for every tight constraint, if the constraint is tight, then all the xij for all I and s, those all have to be strictly positive. None of them are zero. Okay. And so it's pretty easy to actually show that if you have a suitable solution, then you're going to have this nice nested structure that we have shown in this example, where we have one tight constraint of size 2, sorry, of size 1, one tight constraint of size 2, which contains all of the elements of the tight constraint of size 1, and so on. So in other words, if we have a suitable solution, we can just sort of read off from this solution what greedy policy we want to use. Now, the problem we were running into and where we were stuck for a very, very long time on this project is what to do if you don't have a suitable solution, right? So it actually could easily happen that you solve our linear program and then you get something like this, which says the constraint associated with 2 and 3 is tight, but none of the singleton constraints are tight. Okay. But in this case, the definition of suitability tells you, well, so we said before, if we have a suitable solution, the tight constraints are going to be nested. Here, the tight constraints are not nested. Therefore, the solution must not be suitable. What does that mean? That means there must be some set S and some J where this constraint is tight, but one of the X's is 0. So for example, here, suppose that it's X2J is 0 in the optimal solution that we found. Okay. In that case, what we end up doing is we just say, okay, so you're really telling me you don't want to make 2J matches. So we're going to modify our linear program slightly by just enforcing that X2J is 0, but then dropping all of the constraints that involved type 2 matching with type J. Right? So we've dropped all of these constraints from the program, and we now resolve the modified linear program. And when we do that, we can again ask which constraints are tight. And so say, for example, this is the tight constraint that we get. And now that's telling us, okay, J is only going to match to 3, for example. And you might have to repeat this several times, right? So every time you have an unsuitable solution, you can identify a type that is not matching to J, remove all of the constraints involving that type, and resolve. And because we're always just removing matches from the set of possible matches, eventually this process will terminate and we'll find a suitable solution. And once we have a suitable solution, we can just use the greedy algorithm that comes from that suitable solution. So this was really the last key breakthrough we needed in order to prove our result was to figure out how to deal with unsuitable solutions. Okay, the last thing that I was going to tell you about in this video is now we have our linear program. We have a policy or a way to develop an algorithm from that linear program. How do we actually show that this algorithm is good? In particular, how do we show that it beats the performance of the linear program? Okay, so I want you to think of the feasible region of our linear program as defining some polytope. We're not going to worry too closely about what that polytope looks like, but say we have an optimal solution, X star, to this linear program. Okay, now if X star is suitable, we can use it to define a policy pi, a greedy policy pi, and that policy pi comes with its own set of match rates, X pi. And it's pretty easy to show by the same lemma that we had before, right? Because our feasible region was more constrained than the actual constraints facing a policy pi, it's pretty easy to show that X pi is actually going to lie outside of the feasible region. Okay. But we want something stronger. We don't just want to say that X pi lies outside of the feasible region. We want to conclude that X pi has a higher objective value than X star does. And so initially we were hoping that like X pi would just component-wise dominate X star, for example. But that turns out not to be the case. So what we show instead is that if you essentially shoot an arrow from x pi into at x star, that arrow is going to pierce into the feasible region rather than, say, just glancing off of it. And to prove this result, this is where we use our key lemma, right? So the lower bound that I showed you on the previous slide where I was introducing the linear program. Now, once you know, if you accept that the arrow from x pi pierces the feasible region, it immediately follows that x pi actually has a higher objective value than x star. You can see this algebraically, or you can see it geometrically. Algebraically on the left, right? We know if the arrow pierces the feasible region, another way of saying that is x star can be written as a convex combination of x pi and some other feasible point x hat. Right, so that's what this first line of this proof says. X star can be written as a convex combination of x pi and x hat, and therefore taking the dot product of both sides with our reward vector or our reward matrix R, we have this equality. But of course, we know that R dotted with x star is bigger than R dotted with x hat because x hat is feasible and x star is optimal. So in order for this this first equality to hold, it must be that R dotted with x pi is greater than or equal to R dotted with x star. Okay. Again, for those of you kind of more interested or more able to think geometrically, put another way, because the arrow from x pi pierces the feasible region, we know x pi has to lie between these two black dotted lines. And therefore, for any objective function shown in red that is consistent with x pi being the optimal solution, it has to be the case that, consistent with x star being the optimal solution, it has to be the case that x pi has a higher objective value. So I'm not sure exactly how clear that was or how clear that came through, but I'd say the key idea to keep in mind is that we show that the arrow from x pi to x star actually enters into the interior of the feasible region using our key lemma. And from that, everything is sort of easy. Okay, so now I've covered what is our linear program, what is our algorithm, and how do we show that the algorithm beats the linear program. Now, this last step, showing that the algorithm beats the linear program, required the use of some assumptions. In particular, we assumed that for every type that we might match J to, every type in S, they have the same departure rate. Do we actually need that assumption? Well, we don't need that assumption to show that our linear programming upper bounds the omniscient policy. And we don't need that assumption to show that the orange linear program is always within a factor 2 of the black one. Right? So the only place we need that assumption is to show that our blue, our actual algorithm, beats the orange linear program. And it turns out, in all of the simulations we've tested, that turns out to be the case. Right? So all of these simulations do not assume homogeneous mu. In other words, they violate the assumptions of our theorem. But nevertheless, the algorithm seems to work. So kind of the obvious open question for us is to try to show or to verify whether the algorithm always beats LP-alg, even without the assumptions that we currently impose. So that's all I have for you. The key take-home messages are, first of all, that greedy policies actually can be quite effective for dynamic matching. So in many cases, they can achieve an optimal competitive ratio, a competitive ratio as good as any other policy can achieve. And second, this novel proof technique we have, which is to actually introduce a linear program that lower bounds a policy's performance, and therefore that allows us to prove competitive ratios by just comparing the objectives of two linear programs rather than by sort of directly analyzing the stochastic process induced by a policy. That's all I've got for you. I hope you've enjoyed, and I would welcome any questions you have. Feel free to shoot me an email. My email is arnosti, ARNOSTI, @umn.edu.